So dear students, the topic for today is equipotential surface, and so it is defined as the surface where the value of the electric potential is constant at every point of it. So basically equipotential surfaces are the surface in which the value of the electric potential will be constant at every point on its surface. So there are a few properties of equipotential surfaces. So number one is the work done in moving a charge in equipotential surface is 0. Okay, let's take, suppose you have an equipotential surface this way. Suppose this is your equipotential surface. If you do work in moving a charge Q from point A to B, you have an equipotential surface and you are doing a work in moving a charge from A to B, then work done in moving such charges will be 0 in equipotential surface. Number 2 is the electric fields are always perpendicular at every points on the equipotential surface. Suppose you have equipotential surface this way. This is your equipotential surface. So at every point on the surface, the direction of the electric field will be normal. So at such surfaces, the direction of electric field are always normal. Number 3 is no equipotential surfaces intersects with one another. So no two equipotential surfaces intersects with one another. Now we are going to draw the equipotential surfaces of some of the electric charge distribution. Equipotential surfaces of some charge distribution. So next discussion is equipotential surfaces of some electric charge distribution. Suppose you have a single charge. So equipotential surface of a charge looks like this. Suppose you have a positive charge. Its electric field lines are outward in all directions. So these are basically electric field lines of a positive charge. Now if you want to draw the equipotential surfaces for this kind of charge, then the dotted line, okay, firstly, the potential due to a charge is simply 1 by 4 pi epsilon naught q divided by r. So this is the value of the potential due to a single charge, and as you can see, it is an inverse square formula in which the value of electric potential keeps on decreasing as you move farther from this charge. That means as you move farther from this charge, the value of the potential will decrease. And if you draw the equipotential surfaces, you have to be careful, because this potential surfaces will also give you what is the value of the electric potential at each surfaces. Meaning the electric potential surfaces will be closer when it is nearer to the charge, and it keeps on it goes farther away as you move away from the charge itself. So the electric potential surfaces goes farther away. This dotted line, this dashed line are your equipotential surfaces. Equipotential surfaces, and as you can see, the equipotential surfaces are closer near the charges, and the equipotential surfaces are farther when it is farther from the charge. It signifies that the value of the electric potential near the charges are very large. In similar manner, we have discussed the electric field lines density near the charges are larger. That means electric field value near the charges are very strong. In the similar manner, electric potential equipotential surfaces near the charge are very dense. That means the value of the electric potential near the charges are more than the value of the electric potential farther away from the charge. Now equipotential surfaces. Now second is dipole. Let us draw the equipotential surface of a dipole, or electric dipole rather. Electric dipole. So positive charge, negative charge. So firstly we will draw the electric field lines. So this is the electric field lines. This is the electric field lines of a dipole. Okay, let's draw one more. So these are the electric field lines of a dipole. Now if you want to draw the electric potential, what you see is you have to draw the electric potential of two different charges individually. You have the electric potential of this charge and you have electric potential of this charge. But the electric potential, you have equipotential surface of this charge and you have a equipotential surface of this charge. Individually you have to draw like that, but the equipotential surface of this charge will be influenced by the electric potential equipotential surface of this charge. That means the equipotential surfaces will not be like as in before around a positive charge, because it is influenced by the equipotential surfaces of the negative charge. So it is not only the dotted circle around this charge or a dotted circle around this charge, but it is since it is a positive charge and it is a negative charge, so the equipotential surface of this is attracted by the equipotential surface of this charge. That means it looks like this. So this is the first equipotential surface. Now the equipotential surfaces towards this side will come closer to one another, and this side it goes farther apart, because the equipotential surface of this is getting attracted by the equipotential surface of this charge. So here also it is they are closer at this very space, and they are farther at farther space. So they are closer So what is happening actually is the equipotential surfaces are closer towards this side than this side. Similarly, the equipotential surface are closer towards this side than this side, because the equipotential surface of this is getting attracted by the equipotential surface of this. So for a clear picture, you can refer to book. Similarly, two positive charges. You can draw the equipotential surface of two similar charges. So what it looks like, you may have some clue about it. So you have a positive charge. Firstly, draw the electric field lines diagram. Field lines get repelled. Field lines get repelled. So this is the electric field line diagram of two similar charges, in this case two positive charges. Now the equipotential surface diagram of these two charges will be, you have an equipotential surface of this charge individually, and you have equipotential surface of this charge, like this one. But it won't be like concentric circles as in before, because the equipotential surface of this can be influenced by this. And since they are positive charge, so equipotential surface at this side will get repelled this way. So equipotential surface towards this side will go farther apart, because it is getting repelled by the equipotential surface of this particular charge. So it will be simply like this. So in this direction, the equipotential surface are farther apart, because they are getting repelled by the equipotential surface of this charges. For clear picture, you can refer to the book again. So last one, equipotential surface of a uniform electric field. Uniform electric fields. So uniform electric fields, it will be like, suppose you have electric field lines towards this direction. So if you draw parallel planes this way, so these planes are your equipotential surfaces, because at every point on this surface the potentials are potential difference, electric potential is same. Even at every point on this surface, the electric potentials are same. At every point on this surface, electric potentials are same, and at every point the electric fields are perpendicular to every point on the surface. So this is the equipotential surface of an uniform electric field. So the important thing you have to conclude here is, basically equipotential surface is a surface at which the value of the electric potential is constant. So if you have any charge q, so from this q to any distance r, at any distance r, same distance r, all around, at any distance r, from the formula, if distances are same, if R is same, then the value of the potential at those particular points will be constant. So at this point the value of the potential will same, at this point, at this point. So at every point which is at a distance of R, the value of the potentials are same. Even if I draw a distance here, 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 so at every point on such distances, the value of the electric potential will remains the same. That means that surface is nothing but for a single charge. That surface is nothing but it is a circle itself, because for a circle at every distances from the charge it will be the circumference of the circle, because Q is the center of the charge, center of the circle. That means at every distances R, the value of the potential is same. That means this circle is your equipotential surface for 2 dimensions. Therefore, for any charge you'll have a equipotential surface of an concentric circles. Even at this circles, the equipotential circles, the value of the potential is same. So this circle is also your equipotential surface, so which we have already shown in here. If your situation is 3D, for a single charge, equipotential surface are nothing but they are the spheres, because the circumference of the sphere is equidistant from the charge which is at the center. That means at every point on the surface of the sphere, the value of the potential will remain the constant. So one sphere is your equipotential surface, another sphere is your next equipotential surface, another sphere is your next equipotential surface, and so on. And electric fields will be perpendicular to every point on the surface. In this case also, the electric field are outward at every point on the surface. So electric fields are always perpendicular to the equipotential surface itself. So electric fields are always perpendicular to the every point on the equipotential surface. Thank you.